the conductor. I'll not worry about it now. Check it. Total free charge inside the conductor is fixed. I'm coming to that free charge because it is required for us in semiconductor devices as well as conductors here. Because that as a part determines the sigma of that particular material, which is important for us. Consider metal. Any metal. Metals are electropositive in nature. Metallic atoms. Which give the electron out and get the stable configuration. They get metallically, only metal atoms if they are there. Every atom want to give the electron. In the case of ionic bond, there will be transfer. In the case of covalent bond, both are electronegative. Both want the electron. Covalent bond is formed between electronegative atoms. Ionic bond between one electropositive atom and another electronegative atom. Metallic bond, only electropositive atoms. All of them contribute electrons which form a pool of electrons in metallic bonding. The metallic ions get arranged in a given order, leading to the crystalline nature of metals. Crystalline nature of metals. Every metal atom has some valency. One or two or three, right? Valency. V. So, when it has participated in the bond, it would have given the electrons out. Some crystal structure, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic, all those things we talk about. Crystal structures arranged in a specific fashion. There are 7 crystal systems. Some crystal structure with given size of the unit cell which can be repeated to construct, like constructing a wall by using bricks. The basic brick is the unit cell. With size of the unit cell and effective number of atoms. Per unit cell. Given size of the unit cell, right? The volume of the unit cell. Now, metal of some volume Vm contains Vm by volume, given size volume of the unit cell, Vu unit cells. Effective number, let us say N0. Check it once. There are Vm by Vu unit cells in the given volume. And Vm by Vu times N0. Sorry, not and now. Finally, we'll put comma. Vm by Vu times N0 number of metallic atoms and hence Vm by Vu into N0 times valency V, number of electrons, correct? Because each would have given that many. Please check it. We can calculate it because every data is available to us for different metals. We know the structure, we know the effective number of atoms, we know the size of the unit cell. In a given volume, Vm of the metal, this many number of electrons will be there. Because of which, listen carefully. The number of electrons, that is what is important for us. Per unit volume is equal to what? N0 into V by volume of the unit cell. Ultimately, it is that called as N, different for different metals. Number of electrons per unit volume of the metal or semiconductor is always fixed irrespective of whether it is carrying current or not. It is incompressible. I will show also if we inject excess charge carriers, they come out onto the surface. Next, it's a derivation for us. So, different metals will have different number of electrons per unit volume. When you go to semiconductors, every basic semiconductor, silicon, germanium, gallium arsenide, they will give you intrinsic concentration of charge carriers. When you dope it with fixed number of dopant atoms per unit volume, we have the formula to compute the number of electrons per unit volume and number of holes per unit volume. They are given to us. The first thing that I want to know about the conductor or semiconductor carrying the so-called conduction or drift current is the number of electrons per unit volume, which is specific and different for different conductors and semiconductors. Is different for different conductors. And semiconductors also. Everything is coming with the name of conductor here. It is fixed. Any doubt here? Cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic are the structural systems. Okay. Orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic. Clear? We can calculate. In semiconductor, we control by adding dopants. That is the biggest advantage for us. Okay? Now look at it. Slowly we will take up a case.